Hello everyone. I'm Osama Ben Sghair, PhD student at the University of Montreal. Uh, on behalf of the co-authors Wali Sahrawi and Eugene Siriani, I will be presenting our work entitled Fighting Evil is Not Enough for Refactoring Metamodels, Promoting the Good Also Matters. In model-driven engineering, building metamodels is an essential task. It's important for many applications, such as model transformations, building domain-specific languages, and so on. However, metamodels need to evolve continuously to satisfy new requirements or for maintenance purposes. The several and continuous changes on the metamodel may harm its quality by making it unnecessarily more complex, less maintainable, and less understandable, which by its side could decrease productivity, efficiency, and increase fault proneness. Here we present a motivating example. This is a simplified metamodel for bank management systems. The bank here is a central class that could have many branches, ATMs, employees that are either full or part-time. Clients could have either checking, savings, or retirement accounts. This metamodel contains several design smells. Among them, employee, which is a concrete class that should be abstract, since it cannot be instantiated, and it defines its concrete subtypes, full-time and part-time employee. To refactor this smell, we need to make this class abstract. Name is a duplicated feature in employee and client and could be refactored by extracting a superclass for employee and client that contains this attribute. Interest rate is also a duplicated feature, and to refactor this smell, we need to pull it up to the account class. And finally, affiliate is a dead class that is disconnected from the rest of the design. Refactoring a dead class consists of simply removing it. One approach to improving the quality of metamodels is through smells detection and correction, using refactorings as mentioned in the motivating example. However, quality attributes are conflicting. Improving one quality attribute may lead to the degradation of another. Therefore, removing all the bad smells is not necessarily the best option, as sometimes removing some bad smells could result in deteriorating some quality factors. For instance, improving the abstraction reusability of the metamodel by introducing many new superclasses may result in a more complex and less understandable metamodel. So the challenging problem here is how to find the best subset of refactoring operations to apply in order to improve some given quality attributes. In our work, we propose a multi-objective optimization approach to refactoring metamodels. Our approach is driven by the improvement of some quality attributes. The main hypothesis in our approach is that quality should be considered along with design smells removal in the metamodel refactoring process. The metamodels produced by our approach are the result of a trade-off between removing a maximum number of smells and maintaining or improving the values of a given set of quality attributes. For this purpose, we use a multi-objective optimization approach that is computationally efficient. It generates a set of non-dominated solutions that optimize a set of given objectives. These solutions are undiscernible since each solution has better values with respect to some objectives. That the final choice of the best model is left to the modeler according to his preferences and to his context. This is an overview of our approach. It takes as input a metamodel that contains bad smells. A quality model is also given as input, and that is used to evaluate and compare the quality of metamodels. A smells detection module is also used by the genetic algorithm to detect and correct smells, which allows to generate new solutions in each iteration of the algorithm. And finally, our solution outputs a set of undistinguishable solutions that optimize the given quality attributes specified in the quality model. So this is how we formulated our approach. We have two main objectives: optimizing a given set of quality attributes and maximizing the removal of smells. Each solution is a set of smells that should be removed. Similarly, it is a set of refactoring operations if we translate each undesired smell to the refactoring operation that removes it. To satisfy the objectives, we used an SGI2 uh, a multi-objective optimization algorithm to find the best set of non-dominated solutions that satisfy these constraints. Our approach is generic as it supports an equality model that conforms to this quality metamodel. This metamodel is defined as a hierarchy of quality measures. It defines the quality of metamodels using 3 levels of abstraction with mappings from high to lower levels. The quality attributes are the highest level decomposed into quality parameters, in turn decomposed into quality metrics. Quality attributes are high-level concerns such as understandability, maintainability, or extendability, although they are easy to interpret, but they are not trivial to measure. So they could be expressed through medium-level quality parameters such as cohesion, coupling, which could be also expressed using low-level quality metrics such as number of classes, number of attributes, depth of inheritance tree, and so on, that are easy and straightforward to compute. The model defined a quality model that conforms to our quality meta model. For instance, they defined the quality attribute extendability as a linear combination of quality parameters that are modeling concept size, coupling, and abstract metaclass size. By its side, the quality parameter coupling is defined in terms of low-level quality metrics as a sum of A and GM, which is the average number of direct associations with other metaclasses, and ANA, which is the average number of metaclasses from which a metaclass directly inherits. To evaluate the quality of metamodel with respect to the defined quality model given as input, we used a delta, which is a DSL that makes it easy to manipulate metamodels. This code snippet shows how we calculate the number of abstract classes and the number of concrete classes using this DSL. This diagram presents the steps of an SGA2 algorithm. It initializes a set of individuals called population. Then, by applying some specific genetic operators, it combines current individuals to generate new ones. These new individuals are evaluated, then sorted into different fronts according to their dominance. The first front is composed of solutions or individuals where there are no other individuals that are better than these in all the objectives. And the second front is composed of all the individuals where there are no other individuals except from the first front that dominates these in all the objectives. Then the top individuals are selected, and if we reach the termination condition, like specific number of iterations, the algorithm ends. Otherwise, it generates the next population and repeats the afterward steps. A crossover is a genetic operator that is used in NSGA2 and consists of combining two parent individuals to generate new child individuals. This is how we define crossover operator. We use a random cut point, then the first child is composed of the left side of the first parent and the right side of the second parent. And the second child is composed of the opposite. It's composed of the right side of the first parent and the left side of the second parent with duplications removed. The mutation operator is another genetic operator that is used in NSGA2, and it mutates a single individual called parent to generate a child individual. We define the mutation operator as follows. We randomly choose a smell from the parent solution and we delete it to generate the child individual. As a result, NSGA2 generates a set of fronts. The first front is composed of non-dominated solutions or individuals where there are no other individuals that are better than these in all the objectives. The second front is composed of the other individuals where there are no other individuals except the first front that dominates these in all the objectives. We use the first front that is composed of the best and discernible solutions, and we recommend them to the user. The following table presents two non-dominated solutions that we have obtained after running NSGA2 on 5 objectives: reusability, understandability, functionality, extendability, and well-structured. So as we can see, each solution has better values in some objectives, so they are called non-dominated solutions. We recommend both solutions to the user, and we let him choose the best solution according to his preferences and his context. So as mentioned earlier, after running an SGA2 algorithm, we select solutions of the first front to the modeler. We eliminate non-valid refactoring solutions where there are conflicts based on a type error procedure. We translate the list of smells to a list of refactoring operations. Each smell is associated with its corresponding refactoring operation that removes it. The user can then select the most appropriate solution according to his preferences. And once a solution is selected, we generate the refactored metamodel. So this metamodel is an output example of our approach when optimizing two objectives, extendability and maintainability. We see that the dead class was removed, the duplicated feature interest rate was pulled up to the account class. However, some of the refactorings were not applied, such as extracting a superclass for client and employee, as this may result in a more complex metamodel with the new introduced classes. So to evaluate the efficiency of our approach, we conduct an illustrative case study where we compare our approach to two baselines, the initial metamodel and the metamodel with all smells removed. The evaluation was based on two quality attributes, understandability and extendability. For this, we have defined two research questions. The first research question is, how does our approach perform compared to the baseline alternatives in terms of understandability? And the second research question consists of comparing our approach, the performance of our approach to the baseline alternatives in terms of extendability. So we have implemented the detection of 4-bit smells, dead class, classification by enumeration or by hierarchy, concrete abstract class, and duplicated feature. And we have also implemented their corresponding refactorings. In our study, we used the CRM customer relationship management metamodel, which has a number of bit smells. Among them, name, which is duplicated feature in many classes, client, CRM, company, and worker. Internal worker and external worker are two classes that inherit worker but do not add any new features. The smell is called classification by enumeration or by hierarchy. And located element, which is a dead meta class. So this figure shows the CRM metamodel with all smells removed. The dead class was removed, the name attribute was extended in a super meta class called name element, and so on. And this is the metamodel generated by our approach, where just a subset of the smells was removed in order to improve the extendability and understandability of the metamodel. We see clearly that, for instance, the duplicated feature name was not removed, as it could result in many inheritance relations with 4 classes. So in the user study, we divided the participants into 3 groups. And we assigned to each group a different metamodel version. We considered 2 quality attributes, understandability and extendability. And during Zoom sessions, we presented to each participant a version of the metamodel, and we asked him different questions related to these quality attributes. Then we computed the correctness of their responses, as well as the time taken to answer each question. For instance, a question related to understandability might be asking participants about some information already contained in the metamodel. And the question related to extendability might be asking participants to extend the metamodel and add the new features. So here we show the results of the first research question. We show the time that participants took to answer questions related to understandability for the different approaches. Participants took less time to answer while using the metamodel generated by our approach compared to the other versions. An interesting observation is that removing all smells resulted in more effort from the participants to understand the metamodel, and that might be related to the introduction of many new classes that made the metamodel more complex. In the right, we show the correctness results for the responses of the participants to understandability-related questions. And participants tended to answer correctly more often for the metamodel generated by our approach. compared to the all and initial approaches. This is evident in the better precision and recall in terms of median, and also it in the in and also our approach has less variability in the correctness metrics. Overall, participants had a higher comprehension level of the CRM metamodel when shown the refactored version produced by our approach compared to the other alternatives. We had similar results for the extendability quality attribute. Participants took less time to extend the CRM metamodel when using our version compared to the other alternatives in terms of median and dispersion. It is also the case for the precision and recall. Our approach was able to improve the time and correctness of performing extendability-related questions. So we also noticed that removing all smells has worsened the extendability of the CRM metamodel in terms of median compared to the initial version, but it reduced the variability of the correctness measures. However, to confirm and explain more these results, a more extensive evaluation is needed. So to conclude, in our work, we proposed an automated approach based on multi-objective optimization search to refactoring metamodels. Our approach is driven by the improvement of some quality attributes, and the results have shown that our approach improves the understandability and extendability of the metamodels. In the future, we intend to perform a more extensive evaluation involving more metamodels, subjects, and more quality attributes. So thank you for watching, and I would be happy to answer your questions and to hear your valuable feedback.